Interference in the ordinary language usually suggests opposition or hindrance, but in physics we often do not use language the way it was originally designed. Richard Feynman from the Feynman Lectures in Physics, Volume 1. There are various reasons why you would believe the standard solar model. It's a good, robust model, and of course those folks were paying careful attention to these experiments. As the years went by, they refined their model and came up with a new test. In recent years, they came up with a lovely test. If you understand the sun, including the detailed structure of the temperature as a function of the distance in the sun, you can predict the resulting vibrations of the surface of the sun. It's called heliosmolography. Heliosismography. And it's like measuring seismic vibration on the planet Earth, but we are actually watching the sun vibrate. Right. The pattern of the vibration is very sensitively dependent on the solar model. If you change the temperature in the middle of the sun a little bit, you change the pattern of the vibration a lot, and it's working very, very well. It really seems as though we understand the sun, and we certainly know the total numbers of the neutrinos, because we know the total brightness of the sun. Yes. So I think the standard solar model folks defended themselves very well, and we are almost obliged to believe what they are telling us because the data is very robust. So what else could be wrong? It could be a practical physics. Here is a wild idea that people came up with, actually fairly early on in the story. Suppose what I said in the beginning of this lecture, that what the minimal standard model say is wrong. Suppose that an electron-flavored neutrino, which is produced in the nuclear reaction in the sun, is traveling the long travel path from the sun to Earth, and as it's moving along, imagine if it could oscillate in the flavor from an electron-type neutrino to a muon-type neutrino. Now, why would this happen? Turns out, the laws of quantum mechanics say that if you have massive neutrinos, if they are not truly massless particle, this can happen. It's one of those weird quantum things that is really hard to understand, but it comes out of the mathematics. In fact, we've seen exactly the same thing happen before with quarks, right? A dark quark can oscillate in flavor, if you like, into a strange quark. We have observed this phenomenon. It's a quite fascinating phenomenon in the quark world, which we haven't had time to talk about. It works in the quark world because the quarks have mass. The neutrino needs to be massive for this story to explain what's going on, and if they are massive, it's allowed it to happen. The rules of the quantum mechanics allow an electro-flavored neutrino to turn spontaneously into a muon type. In fact, it will turn into a muon type or a tau type, and then back again. It's kind of the cyclic oscillation. Wow, cyclic oscillation! How am I visualizing this? You have a bunch of neutrinos leaving the sun, and they are all electron types because that's what the nuclear reaction in the sun produce. It's beta decay. Beta decay produce electrons and therefore electron neutrinos. Now they might oscillate on their way, and by the time they get to the Earth, half of them might be electron flavored and half might be muon flavored. Every detector that I have described so far was specifically designed to look for the transformation where an electron-type neutrino produces an electron and some other transformation. Wow. If you had a muon-type neutrino coming in, it wouldn't do a darn thing in your detector because it doesn't have enough energy to produce the muon that is needed to produce. muons are very, very heavy particles, so muon neutrinos would just go cruising light through your detector, and the electron neutrino are the ones you would detect. That might explain why you are seeing fewer than you expected, because you are only measuring one flavor. Wah! Okay. It's as if you go to the store and buy a pint of vanilla ice cream. As you are walking home, quantum mechanics takes over and some of your vanilla ice cream transform into a chocolate and some into strawberry. So by the time you get home, you have a Napolitan. You have a Napolitan. I think it's a Napolitan, and if you only like the vanilla ice cream, you say, hey, I bought a pint, but now I only have a third of a pint because I don't want to eat that chocolate and strawberry. It's a slightly weak analogy, but that's the basic idea here. If that's true, how could we find out? What experiment can you think of that would verify that there really are the total number of neutrinos coming out of the sun, but they are simply changing flavor? Right. The Canadians came up with a great idea and they built another one of these underground neutrino detectors. It's in a little town called Sudbury. It's a Sudbury Neutrino Observatory and has a wonderful Canadian acronym SNO. SNO SNOW is designed to make the following detection. First of all, it does the same things as all other detectors did. It can see transformations. It's a water detector, but they also have the possibility of measuring a weak neutral current. Remember that the weak force can manifest itself in two different ways according to the standard model. The obvious way, the way that it's been seen since the 1930s, is where a neutrino transforms into an electron, and at the same time transforms when whatever it's hitting from one nucleus into another. That's a usual beta decay, weak interaction. But Weinberg and company discovered a new force of nature. It's a weak neutral force mediated by the exchange of Z bosons. It's neutral, so there is no transformation. A neutrino just comes in, exchanges the little virtual Z bosons and whacks the nucleus. So transformation happens, just neutrino in and neutrino out. So what do you see in the laboratory? You see a nucleus just happily sitting there. Then all of a sudden, boom! It was knocked into by something invisible. Wow, 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 wow! You can detect the presence of the neutrino by this weak interaction, and all you see is just a little recoiling nucleus which will show up as a little light signal in your detector. So, they built these things capable of detecting, and it doesn't care what flavor neutrino you have. An electron neutrino can bump into you, a muon or a tau type neutrino. It doesn't matter, they will bump equally as strong. It's a low probability event, so you have to be patient. They've been running for over a year, and indeed, they have begun to publish their results. They are seeing the full solar neutrino flux when they look in the weak neutral sector. They are seeing them all, so the sun is, after all, behaving just as we thought. There is a full total number of neutrinos, and it really does look as though some of them are transforming into other types, because when they only look at the electron type, they are seeing the usual reduction. But when they look at them all with this neutral current, they see everything. Yes, because it is visible. So that's big news. Okay, we seem to now have evidence that the neutrinos can change flavor, and therefore, according to the quantum mechanics, neutrinos are massive. So now it's a big experimental effort. there are lots of new facilities being designed coming online to try to pin the story down. I'm sure that in the near and distant future, you will be reading a newspaper article about neutrinos as we discover what kinds there are and what's the likelihood that one will transform into another and what's their mass. It's fun stuff and it's also pretty esoteric stuff. I mean, I know that a perfectly legitimate reaction to all this is to say, well, it's interesting, but do we really care? I mean, why does it matter if the neutrino has mass or doesn't have mass? So let me sort of finishing up here with a discussion of the number of reasons why you might care, ranging from the kind of theoretical to the more applied. Right. The most important theoretical reason that I can argue for why you care is we have this standard model of the particle physics, a framework for understanding the world. It's been around for basically 30 plus years now. It says a neutrino is massless and once an electron neutrino, always an electron neutrino. This would be the first time in my professional career in many physicists' lifetimes nowadays that we would have breaking a standard model. Breaking of the standard model. That's pretty big deal. If you break the standard model, then it means that our understanding of the world is really not complete. And we expect that it's not complete. Wow. So that's exciting. It's a shift in our worldview. It's not a complete destruction of the standard model by any means. The whole picture still holds together. After all, in the quarter sector, we had up and down quarks. They were both massive. Then, in the lepton sector, we had an electron and electron neutrino, and one of them was massive. Shoot! Why isn't the other one massive? It almost seems as though it should be. It seems desirable that neutrinos should have mass. It's lovely and symmetrical and would make the standard model nicer. It was a slight artifice of the physicists of the 1960s to say, well, the neutrino is a massless. They were trying to keep the theory as simple as possibly could do, and by making it simple, they had to make the neutrino disaudable. The massless particle, right? So now, what we are suggesting is maybe the neutrino isn't such an audible. It just happened to be quite right, and it took a while for us to figure that out. So there is this breaking of the standard model aspect that make it interesting to physicists. Right. Then there is a practical aspect, and it's not a practical in the sense of the American consumers, at least not yet. I'm not talking about a neutrino TV. I'm talking about an astrophysical use of the neutrino that nobody had never ever even dreamed of even 20 or 30 years ago. We have now formed the images of the core of the sun using neutrinos. Wow. That's a wonderful tool. It's a tool for other scientists. Now you can start to think of all the possibilities. We can measure the inside of the sun. There is no other way to get information directly from the inside of the sun. The only reason this works is neutrinos are formed in the middle of the sun, and then they have the tiny probability of the interacting, even though the sun is hot and dense. Most of them just make it right to our detectors without hitting anything along the way. In fact, most of them go right through our detectors. That's why we need such a big neutrino detectors. Light is produced in the center of the sun, and it immediately bounces around and gets absorbed by other atoms. It takes 1 million years for light to reach from the center of the sun to the outside. Really? It takes 1 million years for light to reach from the center of the sun to the outside. And by then, it's undergone so many interactions that we are not seeing the middle of the sun. We are seeing the edge of the sun. Right, quite right. You could imagine looking at the supernova and the core of the supernova, something that's unimaginable by regular astronomy, or the center of our galaxy. So it's a tool, neutrino astrophysics. Wow, neutrino astrophysics. This is just now beginning. If you want to do neutrino astrophysics, you really better understand neutrinos. Wow. You can't do neutrino astrophysics and say, well, we are not sure if it has mass or if it oscillates, because you are going to be off in your prediction about the center of the some galactic phenomenon by factor of 2 or 3, unless we figure out what the story is with the neutrinos. So this is a motivation for the particle physicists to get their story straight and figure out what's going on. Right. The third consequence, kind of the very large-scale consequence, is cosmological. Cosmology is a study of the universe as a whole. How did it begin, the Big Bang? How did it evolve to where it is today and where it is headed in the future? It's a big question in a certain sense. Where is the universe headed? Right. Remember, the sun is producing these just gigantic numbers of the neutrinos every second, and it always has been. They are all flying out. Most of them just continue to fly along their merry way in a straight line, past essentially forever, and every star in the universe is doing that. So the universe is just filled with neutrinos, right? So dark matter, dark energy, or could be this one? I don't know. These are an astronomically huge number of neutrinos passing through us, and these are neutrinos other than the ones coming from the sun. There are neutrinos coming all the way back from the Big Bang itself. Wow, so literally I've been feeling the remnant of Big Bang or just Big Bang itself. Now imagine for a moment that these neutrinos have mass, okay? That's a new idea that we're just beginning to wrestle with. If all of those neutrinos have a tiny mass, add up a whole lot of the tiny numbers and you get a big number. Think about the effects on, say, a galaxy. There are a whole bunch of the massive neutrinos floating around. They are going to gravitationally attract, alright? Yes, because it has a mass. Therefore, it has a gravitational field, meaning attracting surroundings. Mass creates gravity as the universe is expanding, and we are observing that it's expanding. All these massive neutrinos are pulling it back again. So if they are massive enough, we don't know yet, but if they are massive enough, they may produce enough gravity to turn around that expansion. Right. So it means there is no expansion at all because the universe is expanding. There is no repel force, there is no attractive force by a neutrino which are inside the universe. So half it, and then we might end up with a big crunch, the opposite of the Big Bang. So the fate of the universe may rest in the hands of this exotic little wisp of the particle. Thank you.